First thing I want to do is one of those homework problems. We had a lot of people, not a lot, I had a lot of people do really, really good. So I don't want to say, oh, everybody did bad. But one of them that I thought more people should have gotten correct, what number was it? Integrating LNX. Which one was that? Integration of LNX, number 11. And I told you even the hint in the problem to do it by integration by parts. Here's an issue, guys. There is no antiderivative known of LNX. I mean, there's not a rule. Of all the rules you've got for integration, there is not a rule for the antiderivative of LNX. There's not one published. So you can do it with integration by parts. It's about the only way that you can do this. Now, I said you need to pick your parts first thing. Your U is something in there that is not as complicated as the other part, but that you can take the derivative of. And then you also pick a dV, which is supposed to be the part that is most complicated, but that you can take the antiderivative of. Okay? So the problem is lnx doesn't have an antiderivative per se. So it's going to have to be your u. So what is the derivative of lnx? It does have a derivative. What is it? Derivative of lnx. 1 over x dx. Okay? So that leaves, as far as parts go, that leaves the only thing for dv is the dx. Not complicated at all, but that's all that's left over for dv. And it can be integrated. To go from dv to v is an antiderivative. What is the antiderivative of 1 dx? X. Okay, the integration by parts rule is, the formula for this is probably what you had written down on your paper, or I hope, is uv minus the integral of v du. That's the way that you put integration by parts together. So here we go. U times v would be x times ln x minus the integral of v, which is x. Du is 1 over x dx. So x times 1 over x, if you multiply those together, you just get 1. So to finish that up, we've got x ln x minus the antiderivative of dx, y'all told me was x, and then plus an arbitrary constant c. That's the antiderivative of ln x. If I were to take the derivative of this right here, this expression, then I should get ln x. If I were to differentiate this expression right here. Product rule, the derivative of x would just be minus 1. The derivative of c would be nothing. So it should work out to check to be ln of x. Okay? All right. So the big overwhelming theme that's going to be on this next quiz is going to be integration or solving by separation of variables, right? A separable equation. More problems of that probably than anything. Separation of variables. Let's review that a little bit. When you're dealing with first order differential equations, first order, separation of variables is probably the big daddy of all of them. It's probably the most commonly used method to solve a differential equation that you'll run into. It's not the only one, but it's probably the most common. Okay? So that's why we spent more time on it than the others. So here's one where we want to dx over dt. In this one, x is your dependent variable, t is your independent variable. So it's kind of like instead of x and y, we've got, instead of y you have an x, instead of x you have a t. So this is going to be your less important, I guess, what you'd say. the t is the x is dependent upon whatever the t is. But as far as just separating these, now if you have a problem that gives you like y prime right there, change it to dy over dx or something like that. To help you separate, that's going to be more algebraically sound for you to do. So this is already in a good form. I'm going to multiply both sides by that dt to separate that out. So dx equals 3x t squared dt. Now, to separate those variables, you want to get anything with an x then on the left side with the dx. Everything else that doesn't have an x involved, you can leave over there with the t's. So on this side, I need to get that x out. So I'm going to divide that off both sides of the equation. Okay, so that leaves me 1 over x on the left side, dx, equal to 3t squared dt. And this is just a real easy one. Integrate both sides. So what's the antiderivative of 1 over x dx? ln of x. ln of the absolute value of x is would be even more correct. We'll just leave that. ln of x equal to antiderivative of 3t squared with respect to t. 3t cubed over 3, which is just t cubed. We'll put the plus c with that side. Now, how can I solve this problem explicitly for x? Instead of having an implicit solution to get x equal to everything. E. So x equals, that e to the ln x just leaves you your x. E to the t cubed plus c. What did y'all remember what we did there? E to the c is just a big constant, right? So c1 e to the t cubed. There's your solution. Now, since my problem doesn't have an initial value, a point, then I can leave the c1 in there. If I had an initial value, then I should not have a c in my answer field, correct? Right? You have an initial value or a boundary value, you should be able to get that out of the equation. And of course, they just get more and more and more complicated. This is just an algebra nightmare is all. On this one, I'm going to move all the x stuff. I kind of like my x stuff to be on the other side. I'm going to subtract all that and leave my y on the left. That's just a me thing. Y'all don't have to do it that way if you don't want to, but I'm going to move all that x stuff to the other side. E to the x squared y dy equals negative x plus xy squared dx. I like my x on the right, my y's on the left. Now to separate stuff, obviously I'm going to have to divide by the e to the x squared on both sides, but also you need to get this right side in a little bit better form. What can we do over there? Take an x out, factor out an x. So factor out an x, that's going to leave me 1 plus y squared dx. Okay, then you can separate your stuff out better also. On this side, we need to get rid of that e to the x squared, so I'm going to have to divide it off both sides. And on this side, we need to get rid of this 1 plus y squared, so let's do that, the whole quantity. And unfortunately, it's still really not very pretty. Guys, I'm going to do something. Because that e to the x squared is down below, does anybody remember anything I can do to kind of help myself there? How can I rewrite that in a different way? Make the power negative, absolutely, and that'll make it come up to the top. So that's going to be minus x e to the negative x squared, absolutely. Because the x squared is in the denominator, I just brought it up and made the exponent negative. So now it's just a pain of integrating. If you work better separating stuff out, like get you a little piece of scratch paper to go over to the side, integrate those, then do so. For example, I'm going to use the board here as my scratch paper. Y over 1 plus y squared, if I was going to do that problem individually, U substitution, right? Will that work with U substitution? You might think inverse tangent because of the a squared plus y squared, but that y is messing me up. Okay? So my u would be 1 plus y squared. Du would be 2y. So you've got the dy, you've got the y, you don't have the 2, so what do you compensate with? 1/2 out front, or 1 over u du. So in that case, guys, what is the antiderivative of 1 over u? Right. Okay, so I said my u was by 1 plus y squared. Du equals 2y dy. So we get 1/2 natural log of, why do I not even need absolute value on that one? 1 plus y squared, is that ever going to be negative? Never. That can never be negative in any way, shape, form, or fashion. So you don't have to have absolute value unless your argument would possibly ever be negative. Okay? That's the only time you really have to have that. 1/2 ln of u, so there we go, equals, let's work on the right side for a second. Is that integration by parts? It favors an integration by parts problem, and that eventually will rear its ugly head. So is this integration by parts? You can do a u substitution. You sure can. What would your u be? Wait a minute. X squared. U would be your negative x squared. I wrote that 2x down, then I confused myself. Oh, this is integration by parts. But this will work. Du then would be negative 2x dx. I have the dx. I have the x. I even have the negative. I don't have a 2. So my compensation will be the 1/2 integral of e to the u du. Why do I not have to do the negative 1/2? You already had that on that side. You already had your negative over there. So that's going to equal positive 1/2. What was the antiderivative of e to the u? E to the u. So e to the negative x squared plus c. Okay. Now I want you to get some common sense going here with this. Now, I had to look at it for a long time myself, so that's okay. Why can I not do the e thing on a problem like this? You'd have e to the e. That's not going to make anything pretty, is it? It's not going to help me at all. What can I do? Algebraically, do y'all see? We can clear the fractions out, multiply through by 2, so you have a better answer would be natural log of 1 plus y squared equal to, if I multiply that first, that's e to the negative x squared. If you multiply c by 2, you still get a constant. Everybody agree with that? So we're just going to call that constant c1, and we're going to leave our answer as an implicit solution. Implicit means you've got both variables present. You didn't solve it for one specific variable. Why would I not keep on trying until I got it solved for y here? I really don't know how. Now, I don't think it would be any better. You did e to both sides, you're going to have e to the e. That's just not good. So this is good enough right there. That's an implicit solution. And when you run into that issue on a test yourself or a problem, just stop. Okay? If it's solving for y or solving for x is that big of a deal, don't keep on and keep on. Unless we see a direct path. Okay? Because I'd rather y'all stop and not make as big of a mess of it as if you kept on and did something silly and messed it all up. Let's try one more, and then we'll switch gears just a little bit. I'm going to pause right now and let you guys see what y'all can do with that. Just separation of variables. Try it on your own first, and then we'll tear into it. And this is an initial value problem also, so when we get through, we can't have C in our answer. All right, so I'm going to multiply dx on both sides. Separate things, I need to get this quantity of 1 plus y squared off of this right side, so 1 plus y squared. All right, if I integrate both sides, who knows the integral of 1 over 1 plus y squared? What's that going to have to be? It is inverse trig. If you try to do a u substitution here and say u is 1 plus y squared, your du would be 2y. You don't have a y in there for compensation. That pattern follows the inverse trig. It's actually inverse tangent, right? What is your a value here? A value would be 1. This would be like a squared. So a would be 1. And your u squared would be your y squared. So this is actually going to be tangent inverse of, it's actually 1 over a. So 1, tangent inverse of u over a. So y over 1. So that's it. Tangent inverse of y. Equal to, now I've got this one written down. I try not to look at it. What do y'all have written down as your integral of tangent? So that's one that you definitely want written down somewhere, right? To look up. Plus C. Okay, so a lot of times the question also is, what would it be better to do? Solve right here and find my C, use your initial value to find C in this step, or go ahead and, that one could be easily solved for y, couldn't it? It actually, you could solve that one for y pretty good, easy. Tangent of both sides will undo tangent inverse. Tangent of both sides will undo the tangent inverse. Let's go ahead and find C. Y of 0 equals radical 3. So this is tangent inverse of radical 3. Negative natural log of cosine of 0. Okay, using your calculator, what is tangent inverse of square root of 3? $60, but I can't write 60 down. That was totally wrong. It is 60 degrees, you're right. What is 60 degrees? What's the radian value on that? Pi over 3. 60 over 180, reduce that. That's how you do it. Pi over 3. When you're dealing with real numbers, you want radian answers there. Okay? What is cosine of 0 in radians? It's 1. What is natural log of 1? 0. So this all goes to 0 right there. So C is equal to pi over 3. So let's go back to right here. We're going to plug it in right there. So I have tangent inverse of y equal to negative natural log of cosine x plus pi over 3. So again, to solve that equation for y, I'm just going to take tangent of both sides. And I don't have a C because of my initial value. That's your solution. It's not terrible. Only horrible, I put that example in there because both of your antiderivatives, when you integrate both sides, are weird things that we don't commonly know. Now, what if all I know about solving a differential equation at all, my whole repertoire is built around either integration, straight out integration, or separation of variables? That's all we know at this point. We don't know any other techniques. What if my teacher threw a problem at me and they said, okay, with what you know, I want you to solve this equation, and there's absolutely no way to separate the variables? This leads into the concept of what we call a first-order homogeneous equation. First-order homogeneous equations. We're going to hear that word again later, and it means something different. Right now, with first-order equations, homogeneous just means it's like a separation of variables question. You can't separate the variables. We're going to make a substitution. Sometimes it's impossible to separate the variables in a differential equation. However, it might be possible to make a substitution that would make it possible to separate. This occurs in the homogeneous equations. If you are given a DE, if the right-hand side of the equation can be expressed as a function of the ratio y over x alone, that requires some algebra there to manipulate that all, then we say that the equation is homogeneous. These are kind of difficult, guys. I'm going to be nice to you and tell you when it's a homogeneous equation, when to use that method, okay? They're going to try to make you figure that out on your own. You probably would be able to, because when you tried to separate stuff algebraically, you just could not do it, okay? For example, this is a homogeneous DE. If you were to solve this and getting your dy over dx together, you're left with y minus x over x. And notice, if you have an expression like that, you could divide that x out of each term individually, y over x minus 1. If you can algebraically make your function in terms of something y over x, that makes it a homogeneous equation. That's a proof for a homogeneous equation. Another test for homogeneity, is that word, is to replace x with tx and y with ty. then the equation is homogeneous only if f of tx and ty will equal the same thing as your original function, by putting a t in there with it. Here's the method that we're going to use to solve these in here. We're going to make this substitution right here. V is a new variable we're going to come up with. V is equal to y over x. That's one thing you want to make sure you put in your note. V equals y over x. But to make this transition more smooth, what we're going to do is, if you were to cross multiply right here, v times x is equal to y. Everywhere in my problem that I have a y, I'm going to substitute in vx. Everywhere I have a y, I'm going to substitute in a v times x. So, if I have y equal to vx, if you wanted to do dy, the derivative of y, this is a product. Everybody agree? Product rule, f prime g plus f g prime. F prime would be dv times g, which is x, plus f, which is v, g prime, the derivative of x, which is v dx. So everywhere you see a dy, you're going to put in x dv plus v dx. This is what you need to highlight, circle, whatever. When you do that substitution, what you're going to be able to do then is separate your variables. Separate your v's, separate your x's. That will allow separation. And then when you get done, when you've got any v's left in your answer, you're going to substitute any v's with y over x. That will help you solve your equation. You're going to go back and resubstitute any v's you got left over with y over x. These are hard. Stick with me, okay? These are difficult. These are probably some of the hardest ones you're going to do all semester. So, let's start off with a good one. So everywhere I have a y, what am I going to put in? X times v. And everywhere I have a dy, x dv plus v dx. You're going to make those substitutions every time in a homogeneous, first order homogeneous equation. So here we go. On the left side, y squared, that would actually be x squared, v squared. Y squared actually would become x squared, v squared. Plus y times x, go ahead. Because it would be like saying this. Well, you'll want to separate that out, though. That rule right there just means you raise everything in that power, in that parentheses of that power. Right? You'll want it, and you'll want to be able to, when you're separating, you'll want it to be that way. All spread out. X squared, v squared, plus y times x. So think about some algebra in your head here. X, v times another x. That's going to be x squared, v. dx, I don't change it at all. We leave it the way it is. So everybody get that step right there. xv times another x will be x squared v. Minus x squared times, instead of dy, what we're going to put in is this, x dv plus v dx. Equal to 0. A lot of algebra. A lot of algebra here. So let's clean it up. Let's clean our algebra up. And I want to separate my dx's and my dv's with all the terms. We'll put all that together, okay? So I'm just like, on this part right here, we're going to distribute this dx. So I've got x squared v squared dx plus x squared v dx. On this one, we're going to distribute this minus x squared times that stuff, so that'll be minus x cubed dv minus x squared v dx equal to 0. Anybody see anything good? Any good algebra? Those zero out, don't they? Yay. Cleaned it up good right then. So I've got x squared, v squared dx. And I'm going to move this other term, since it's a dv, I'm going to move it over by just moving it up to the other side here. So equals x cubed dv. Just add that to the other side. Then separate your variables. What do I need to do to separate, guys? What do I need to divide on each side? On the left side, we need to divide off the v squared. What about the right? The x cubed. So crossing stuff out, leave me 1 over x there. On this side, the x cubes go, and I've just got the 1 over v squared dv on that one. No big deal. So that's going to leave me 1 over x dx equal to 1 over v squared is the same thing as what? V to the negative 2. Good. Okay, integrate both sides. The antiderivative of 1 over x dx is natural log of x. What would the antiderivative of v to the minus 2 be? Yeah. Try to put it together. That's your complete answer. I was thinking the process, and you're exactly right. V to the minus 2, if you add 1, you get v to the minus 1. Divided by minus 1, right? So it'd be negative 1 over v plus c. Everybody, if you didn't see that, let's review that. V to the minus 2. Integral of that, you add 1 to the power. So it'd be v to the minus 1. Divided by minus 1. This makes it negative. This flips it. Antiderivative. Okay, guys, we are cooking with gas so far. Let's see what we can do to clean this up a little better. Ln of x equals negative 1 over v. Anybody got any suggestions on that? Can we go ahead and make our substitution for v now? What is v equal to? V is equal to y over x. Y'all remember that was one of our first? But 1 over v, what would that be? 1 over something. X over y. It flips it. 1 over something flips it. So that would become x over y. And the negative also would be minus x over y plus c. Now here's where y'all have a lot of questions. Y'all are like, do I need to keep on going with this? Do I need to try to solve it for y? This one is very possible to solve for y. What are you going to do to solve for y? Say what? Okay, multiply through by y. There's where you got a problem. Look at that. But you got to multiply that, right? Now what, guys? Multiply through by y. Can I get the y all on the left side and everything else on the right? Can we divide a y? Can we factor out a y on the left? Am I going the long way around the tree here? Did y'all see something easier than what I'm doing? Sometimes I'm known to do that. So ln of x minus c and then I would just divide that out both sides. So I would say that my explicit solution Austin, did you see something I should have done? I could have shortcut instead. Was yours a shortcut? Not really. I think you must teach you how to work over it, but I do a lot of times do it the wrong way. I had to draw some back to those centers. Oh, okay. Okay. Oh, because you have your 1 over y. 1 over y equals something. The y was equal to width. Yeah, that's a good idea. Real good idea. Questions? It's heavy on algebra, guys. That first substitution step is what you got to get. And my mistakes, when I do this for myself, if I'm working a problem by myself, the mistakes that I make are little silly algebra exponent moves and stuff like that. Or writing something down wrong. Okay, be careful on that. That's where you're going to get, where you'll lose it, for sure. Let's do a hard one. A sure enough hard one. Again, we're going to make our substitutions. For every y, we're going to put in an x times v dy, x dv plus v dx. So let's see what we got here. Minus xv dx plus x plus the square root of x times y, that's x times v, so x squared v times dy, which is x dv plus v dx, I'm scared, equals 0. Okay, before I start multiplying anything out, does anybody see anything I can do algebraically? Kind of help me out maybe here a little bit, possibly? We're going to have to FOIL, yes, you're right, but anybody see anything I can simplify before I start doing all that full mess? Could this radical simplify? The square root of x squared v? What's the square root of x squared? Can I pull an x out of that radical? Then I just have the radical v part. I'm just thinking that might help a little bit. Let's see what we got here. Negative xv dx. Okay, I'm going to FOIL like y'all said. Plus x squared dv plus xv dx plus x squared radical v dv plus xv radical v dx. Does anybody see anything good there? Okay, I've got all DV. I'm going to leave all my DV stuff on the left side. All my DV stuff, I'm going to group it together. These two terms. Move this dx stuff to the right. And that should be minus. I'll move it over there. What about any factoring or anything? Okay. Separation, divide by x squared on both sides, and by v radical v on both sides. How hideous. If you love algebra, this is your kind of problem. If you don't love algebra, then you are in mess on this one. How else can I write this right here? Anybody got an idea? Good job. That's b to the 3 halves. This is b to the 1 half times b to the first. The powers, if you're multiplying together, you add the powers together. That would be b to the 3 halves power. B to the 3 halves. And that's all just one term. So I can divide that individually out of those two right there. Take this, the one divided by that, and then this divided by that. Individualize. Right there. Split it up. That's going to be how you get out of that. So this would actually end up being 1 over v to the 3 halves plus what now? Yeah, since they're both v's, I can keep it that way and just do them separately. 1 over v to the 3 halves, and then this other would just be 1 over v, right? dv. Radical v over v radical v, that would just give me 1 over v. And then on this right side, I'll end up with negative 1 over x dx. Let me make sure I gave myself some room here. I did, yay. So here's the hard part. Let's go to my chicken scratch board over here for a second. Get you integration bridges on. V to the 1 over v to the 3 halves is the same thing as what? V to the negative 3 halves. So integrating that, that would be add 1 and then divide by your new power. So this would be v to the Negative 1/2 divided by negative 1/2. What's dividing? The same thing as dividing by a half. Multiply by negative 2. So this is going to give me, for that first, that part will be negative 2 v to the negative 1/2, that's going to be, y'all agree with that? For that term. Just for that one little term, that's the antiderivative of that. Okay, that's just this one right here. What's the antiderivative of 1 over v? Natural log of v. Good job. Was that plus? Absolute value of v. I'm not going to fool with the absolute value. Okay, ln of v. Okay, equals the antiderivative of negative 1 over x. Yep. Oh, not dx, but what? Plus c. Okay. I am now going to put in my substitutions. What are we going to substitute for v? Y over x. Y over x. So negative 2 over the square root of y over x plus natural log of y over x Who remembers from algebra days, if you have the square root of a fraction, that means the square root of the numerator over the square root of the denominator. So I have a complex fraction going right here. We can flip this one, right? So it's going to be negative 2 square root of x over the square root of y. But don't worry about any of that rationalizing the denominator stuff. Don't have to worry about that. This will be negative 2 square roots of x over the square root of y. How can I bust up ln of y over x? How can we break that up? Do you remember that rule? You have a quotient, you can separate it by subtraction. I wouldn't have done that except for this step right here. Who sees something I can do algebraically? Those are gone. Okay. This is not going to be one that we can solve explicitly, I'm almost positive. Or at least not for y. We might can solve it for x. So, suggestions. Okay, let's do it this way though. Do that first. And then we're going to square both sides like they said. Y'all got me doing all kinds of crazy stuff. Let's see here. That's going to be 4x over y equal to to make me look like I'm smart. You don't have to. You can get away with not doing it, but I do it just to make myself look like I'm intelligent. That's it. That's a really good explanation too. Okay, now what? Anything else? I'm really not being a smarty pants when I say that either. It really does just make me look more mathematical, I think. It's just naming my constants. Y'all had problems with C1s and C2s and C3s. These, of course, you would just have the one issue going on here. I can do better with this. What would we need to do? Multiply by y? So we just keep on. We won't kill this one. 4x equals y times C1 minus ln y squared. And somebody said what? You could divide it by 4. I've been told by my cohorts that I teach with here that I'm a show-off. I don't believe them. That I like to put on a show. Y'all see if y'all can help each other on this one before we have a break. All right, let's do one more of these before we switch gears a little bit to something a little easier. This is another one of those homogeneous. I want to show you something before I tear into this and to show you a proof that this is homogeneous. It kind of showed you this at the beginning. But if you were to divide each of those terms individually by that denominator, and so, to simplify that, this would be 2y over x and this would be x over y to the third. X cubed over y cubed, which is x over y to the third. Notice you got those x over y or y over x. You can write it you can write it in terms of y over x or x over y. That's writing it in terms of v. Actually, what you're doing. Now that's just a proof that shows this is a homogeneous, first order homogeneous equation. But I think our methods that we learned previously are going to help us more. So let's go ahead and do those substitutions. Instead of y prime, what are you going to use? dy over dx. And you can cross multiply also. But first of all, y is equal to xv. dy is x dv plus v dx. So if I say that dy over dx equals 2y to the fourth plus x to the fourth over xy cubed, I can cross multiply because that's like a proportion. So you would have xy cubed dy equal to 2y to the fourth plus x to the fourth times dx. Just cross products. Okay, so making our substitutions, x times y cubed would become, let's try to do that in our head. I'll write all that steps. Y cubed would be x cubed v cubed. So times another x, that's going to be x to the fourth v cubed times dy, which we know is x dv plus v dx, equals y to the fourth will be x to the fourth v to the fourth. So 2x to the fourth v to the fourth plus x to the fourth dx. Distribute on the left side, so that's going to be x to the fifth v cubed dv plus x to the fourth v to the fourth dx equal to, on the right side, you're going to distribute the dx, so 2x to the fourth v to the fourth dx plus x to the fourth dx. Before I start trying to separate anything out, is anything see anything algebraic that can happen here? You could, or could we just not just subtract it anyway and get rid of that 2 altogether? See what I'm saying? Take this one away, it'll just make that one of those then. So let's do that. X to the fifth, v cubed dv. I'm going to subtract this term here from both sides. So equals, that's going to leave me with one of them on the right side. That right side needs to be cleaned up a little bit. We need to do some factoring on that side, looks like. So what can I do, guys? X to the fourth. So I have v to the fourth plus 1 dx. Okay, separation. We're going to take out the x to the fifth off both sides. And the v to the fourth plus 1 quantity off both sides. And I can get some simplifying here. So I've got v cubed over v to the fourth plus 1 dv equal to 1 over x dx. That's funny that it always seems like we get 1 over x almost every time. Think about it for a second. Integrate both sides. The right side we got, no problem with that. How am I going to integrate the left side? U substitution, what would U be? Du then would be 4 v to the third dv, which I've got the v to the third. I don't have the 4, so I'm going to have to do the 1/4 thing. So 1/4 natural log of u to the v to the fourth plus 1. Sorry. That's another one that you wouldn't need absolute value bars on. V to the fourth plus 1 is always going to be positive. And this side will be what? Natural log of x plus c. Okay, we got to learn something here. can I do? Multiply both sides by 4. You could do that. Okay. Now what? E it? Okay, I'm going to E the thing, like y'all said. Y'all are exactly right. But you got to be careful right here. We'll get some algebra rules and logarithm rules messed up. What is that 4 in front of the ln x going to become? What was the logarithm law that we had when we could pull a number in front? It's an exponent. That is an exponent. So what would happen there is you're just going to be left with v to the 4th plus 1 equal to e to the 4 ln x becomes x to the 4th power. The number that's been pulled out front was actually an exponent. Okay? So this is x to the 4th. And the c became what, though? I forgot about that. C1x to the 4th. Okay? So v to the 4th, what that would actually be what? Y to the 4th over x to the 4th? I'm going to pause this for just a second. Okay, so now what, guys? Can I multiply through by y, x to the 4th, I mean? Multiply everything by x to the 4th. X to the, C1x to the 8. Okay? Is that okay? Can we solve this one for y? Fourth root, or you could raise it all to the 1/4 power. Yes, sir. Okay. Got a plus 2 right there. Now I got the v to the 4th plus 1 on this side because I factored out that x to the 4th. Questions, guys? Anybody? If I had put that all in parentheses to the 1/4 power, that's the same thing. And that might maybe even be an easier derivative to take. Now, if you're a huge nerd or you got a whole lot of time to be working on this stuff, what you could do, here's y. This is what y is. But I could do all this. I could find the derivative of y prime or dy over dx, the derivative of that. Go back over here and plug it in here and see if this is true. If you got a lot of time on your hands, you could do that. Okay? Hard, but you could do it. Okay. Another type of first order equation that I want you to look at here is what we call an exact equation, and this is easy, easy, easy. These are probably the easiest ones you've seen so far. An exact equation uses Cal 3. We haven't done much with Cal 3, but we're going to go back to the concept of a partial derivative or a partial integral. Okay? You guys kind of did something with like this in Cal 3 when you had to determine whether a vector field was independent of path. You had to find a function, a conservative vector field, or a potential function. This is not even related to that same concept, but it's very related to the process of how we did it. Another type of first order ordinary differential equation is an exact equation. So that's what we're looking at here. This is another example of when separation of variables will not work. The form of your exact equation is going to be like this. Some function in x and y, mixed up x's and y's, dx, plus some function of x's and y's, dy, equal to 0. We want this to be the total derivative of some mystery function. You're trying to find that mystery function, and you're going to set that mystery function equal to a constant. You have the derivative of a function set equal to 0, which is this, and you integrate each side. If you integrate the derivative, you get the mystery function. But if you integrate 0, you get some kind of constant. Think about that. If you integrate a number, you get you have to add an x to it. If you have nothing to integrate there, you get a constant. The derivative of a constant would be 0. So what you're going to do is once you find this mystery function, f of xy, you're going to set it all equal to c at the end. Okay, that'll be your constant. So, got a bunch of proof and stuff right here, and I'm not going to go through all that and bore you to tears. But y'all see the little swirly looking d's there. That means partial derivatives. What they're saying is that original dE, if it's an exact dE, they're saying that the partial derivative with respect to x, dx, is going to be the form that you're going to be following here. Whatever's in your parentheses with the dx ends up being the partial derivative of your mystery function with respect to x. And the part in front of the dy becomes the partial of the mystery function with respect to y. Your m of xy, your n of xy. The test for the exact dE, this is what you need to know. If you can take the partial of m with respect to y and get the same result as the partial of n with respect to x, that is a proof that it's an exact equation. Your m is going to be in front of your dx, your n is going to be in front of your dy. A lot of stuff there, but it's really not that complicated. I'm going to show you an example that'll make it hit close, more to home to what you're looking for. We want to first test for an exact dE. Only integrate one part of the equation. Choose the easiest part to integrate. Instead of leaving an arbitrary constant, you'll have a function in another variable. Differentiate the new function with respect to the other variable. Compare the result with the other part of the original dE. Solve for the arbitrary function. Lastly, set your complete f of xy equal to c, as we stated in the beginning. Okay, that's a bunch of bull to read those steps right now. So let's come back to it. Okay, let me show you what to do, and then we'll come back and look at these steps again. Here's the problem. If I want to test this and say, is this an exact differential equation? What I'm going to do is I'm going to pretend that this part is the m, and the part with the dy is the n. So the test says this. Your partial of m with respect to y has to equal your partial of n with respect to x. That has to be true. So in this case, let's see if that's true. On m, what's your partial derivative of m with respect to y? The 2x you're going to ignore, right? So 3. Now look at the other part, n. What's your partial derivative of n with respect to x? 3. So guess what? That's an exact equation. That's the test. That is an exact equation. So here's the steps. If it's an exact equation, take one part of it. This looks like the easiest one, 2x plus 3y. And we're going to go backwards. We're saying that this part right here was the partial with respect to x. So I'm going to anti-differentiate it with respect to x. Okay, if we integrate that with respect to x, tell me what we would get. Okay, 2x squared over 2, so y'all said x squared. Good. Plus, if you just anti-differentiate 3y with respect to x, you're just going to stick an x to it, right? I think y'all said that. 3xy. But it possibly could have been just some kind of y function, right? So plus some function, we'll call it g of y. We don't know. Don't put plus c, but just some kind of function y we don't know. Now, I've got this. Guess what, guys? This is potentially my answer. This is potentially the answer to the whole problem right here. We don't know what this part of it is. So we got to work with that for just a second. So what I'm going to say is, let's take the partial derivative of this with respect to y. This is possibly my f function right there. So the partial of f with respect to y, what would that be? What's the derivative of this with respect to y? The derivative of x squared with respect to y would be nothing. What about this? 3x. Good job. What would the derivative of g of y be? G prime. Somebody say that? G prime, just g prime of y? Now I want you to compare that with what you got up here. This 3x plus 5y squared. So the 3x's were equal to each other. Cross those out. So we say that g prime of y is equal to 5y squared, guys. How can you go back to g of y? If I know that the derivative is 5y squared, how can we go backwards and find g of y? Integrate. You just flip-flopping and flip-flopping here. What's the antiderivative of 5y squared with respect to y? Five y cubed over 3. Very good. So where am I going to plug that back in at? So here's your solution, your general solution to this equation. Is x squared plus 3xy plus 5/3 y cubed equals C1. That's the general implicit solution to that exact equation. Yes. Just make sure if you do that, though, that you do right. You're integrating with respect to a different rule. Just reverse your thought process. He's talking about, could we have started out with this instead? Sure, but you just integrate in a different pattern. Yes, should. You want to try it and see? You want to just test it for a second? Let's just run through it real quick, but I just want to make sure that y'all see the process. So I integrated the first part with respect to y. That would give me 3xy plus 5y cubed over 3 plus possibly some function of x, right? Hopefully something that would just have x in it. Not c, but some function of x. Now if I take the partial derivative of this with respect to x, that would be 3y, nothing. The derivative of h of x would be h prime of x. So compare that to what you had in your original right there. 2x plus 3y. Okay? Those are going to cancel out. So you get h prime of x equal to 2x. So what would h of x be? Squared over 2, so x squared. You're going to get the same thing, right? Don't look out of order, but it's still the same terms. Okay? So let's look back there. Test to see if it's an exact differential equation. Integrate only one part of the equation. Choose the easiest part to integrate. Sometimes you may have a more complicated problem than what we just had here. Okay? Instead of leaving an arbitrary constant, you'll have a function in the other variable. So notice I said possibly something in just x, or g of y, something in terms of just y. Differentiate the new function with respect to the other variable. Compare your result with the other part of the original differential equation. Solve for that arbitrary function. So I've solved for the h of x. Replug it back in and said, last step is to set the whole function equal to c. So that's where your constant c comes in. I have a hard time following just step-by-step instructions like this. It makes more sense for me to actually see it applied first and then go back and look at the steps. I want to see it put in the actual problem first. Okay? Try this one. Now this is a little different because you got this minus sign right there that's distributing across, so you want to be careful with that, okay? That's kind of like having minus sine x, minus sine y, or minus sine x, minus sine y, and then minus 2y. It's kind of distributed across that. So my partial of m with respect to y has got to equal the partial of n with respect to x to prove that it's an exact equation. So if I took the partial derivative of this one with respect to y, cosine of x is just a constant. The derivative of cosine y would be minus sine y. So this would be minus cosine x, sine y, and then the derivative of this with respect to y would be nothing. Equal to, on this over here, this n. Now remember, you got to take the minus sign with it also. Partial of this with respect to x. The sine y is just a constant. The derivative of sine of x would be cosine x, but the minus sign would make it negative. So minus cosine x, sine y. Check. It is an exact equation. It is an exact equation. So, of course, I am going to integrate just the first part because I don't know why one don't seem more simple than the other. So, Now we're integrating now, so you got to be careful. Partial integration with respect to x. Cosine of y is a constant, right? So you don't worry about that. What's the antiderivative of cosine x? It's just sine, I think. You'll think you're right. So sine x, cosine y. Okay, what's my antiderivative of 2x? X squared plus possibly some function in g of y. So this is almost my potential answer right here. I've almost got it all together. We'll call this big function f. Okay, so a partial of f with respect to y, we're going to take the derivative of this thing I've got here with respect to y. The sine x is going to be a constant. The derivative of cosine is going to be negative sine. So that would be negative sine of x sine y. The derivative of x squared with respect to y would be nothing. And the derivative of g of y would just be plus g prime of some y function we don't know. If we set that equal to what we've got up here, negative sine x cosine or sine y minus 2y. Make sure you put minus 2y because that's actually that minus sign right there needs to be distributed. So you can see that those cancel out. So I get actually that g prime of y is equal to negative 2y. So g of y negative y squared. Where am I going to take that, guys? So I got my general solution now. Sine of x cosine y plus x squared minus y squared equals constant 1. Okay. So it's time for a test, right? Time to test your knowledge. Test your knowledge. Y'all think y'all got a grasp on this? I think this is easy. Do y'all think this is easy? Kind of, sort of. Only thing is your brain's going to be switching back and forth. Derivative, integrate. Derivative, integrate. Back and forth. Flip-flopping in the process. So if you want to go back and look at your notes, do so. But here's your work together. Y'all try to help each other if you need to. This one's tough. First time I test you on this, I'm going to say this is an exact equation. Okay? I'm not going to make you do the test. I'm just going to tell you this is an exact equation. I want you to, as we progress, then I would expect you to be able to, just by looking at it, kind of know that's what the process is going to be. But right now, I'm going to tell you that it's an exact. So if I were to integrate this first part right here, with respect to x, you guys know that the integral of e to the x is just e to the x. The sine of y is going to stay like it is. If you're integrating with respect to x there, it's just a constant. And the integral of negative 3x squared would be minus x cubed. 3x cubed over 3, so minus x cubed. Plus possibly some function that is just in y variables. So this is my potential answer here. So do the derivative, partial derivative of f with respect to y. That way we can compare it to that other part. So if I do the partial of f with respect to y, looking right here, e to the x is a constant. Sine of y, the derivative would be cosine of y. The derivative of this with respect to y would be nothing. And this would be g prime of y. Compare that to this whole second term, this n term here. So this would be e to the x right? So obviously those are equal. So g prime of y is 1/3 y to the negative 2/3. So if I want to get g of y, I'm going to integrate that, which is scary looking. Okay, how do you integrate something? Add 1, divide by the new power. So negative 2/3 plus 1, or plus 3/3 would give me y to the 1/3, right? Divided by 1/3. If I divide that by 1/3, what happens to the 1/3? They go away. So that's just going to be y to the 1/3 there. Good job, Mitchell. So we're going to put that back in up there. So my general solution for this will be e to the x sine of y minus x cubed plus y to the 1/3 equal to my C1. On a test, I would tell you this is an exact equation, so use that procedure. Now, you guys are getting a cheat sheet on these tests, right? One full sheet of paper. I think it would be very foolish to not have two things on there. First of all, I would have my integration and derivative rules that I don't know well written down, and I would have some worked examples on those sheets of an exact problem, of a homogeneous problem, of a separation of variables problem, okay? And label that that's what this is. Because you get on there and you go blank, you get on a test and you go blank and you're like, I don't remember what that was. Well, you've got something in front of you to help you remind you of what you're needing to do here. When you guys get in engineering school, that's what you're going to have to do. You're going to go back and you're going to pull a book down, or you're going to pull these notes back out and you're going to be like, how did we do that? You need something to go by. In real life, that's what you do. You go back and look at another example of what you did before. Okay? So make sure that you put that make a good cheat sheet. I want to show you one more type tonight, and we'll be through. But this is a big deal. This one is a big deal. This was number 2 in order of importance. Separation of variables is number 1. It's what you're going to see most of the time. Number 2 is a linear first-order differential equation. How to solve with an integrating factor. Solving with an integrating factor. This is a little different. I will finish this lecture 4 stuff up next week because I'm not going to finish it tonight. I'm not going to kill y'all. Y'all probably need to do push-ups right now, right? We need to get out and do push-ups or jumping jacks or something. I hate that I'm lecturing to you the whole time, but that's about all I can do with this class. Solve using separation of variables. I'm not doing that tonight. I'm doing that first thing next class. Solve using homogeneous. I'll do that first thing next class. An exact, I'll start class off with that one. So let's do this. Linear first order DE. What is an integrating factor? This is, we spent some time in the previous lectures determining whether a differential equation was linear or non-linear. Y'all remember that? These are just going to be linear. first order, this is how you use this integrating. An integrating factor is something that you multiply an equation by to change it from a form that you don't like to a form you do like. That sounds very simple, but that's exactly what you're doing. This is the basic format of a linear equation. Y prime, or your dy over dx, you'll have one term with that in it. You always want to have a coefficient of 1 here. If this doesn't have a coefficient of 1, then you need to do something to get it to be a coefficient of 1. Fix it. Divide through by whatever or something. You want that first derivative with no coefficient. You will have a coefficient in front of your y variable. And then your q of x, this over here is going to be some function of x. Remember, it can't have a y in it, or that's nonlinear. It's got to be just some function of x there. When you get your equation in this form, then you can use the integrating factor technique. So before we do that, y'all tell me if these are linear or nonlinear, or no, these are never mind. These are not questions. This is just examples of linear equations. So this one, you got your y prime, coefficient of 1. That's perfect. You like that. Your p of x is whatever's in front of your y. So 5x would be your p of x. Remember, you're trying to write them in this form. And your function of x over here is this, all this conglomeration of all this mess right here. Notice there's no y's over here. Now, is this one in best form? Tell me how I can fix that one to get it to where something we like. Divide through by x or multiply through by 1 over x. So he said y prime minus 3 over x times y. Then that would be x squared e to the minus 2x. That's better. You want that derivative to have a coefficient of just 1. Now, if I were going to tell you to solve an equation like this on a test, what instructions do you think I would tell you? It's going to say solve the linear differential equation. That's what you're looking for. That's the key word you're looking for. Solve the first order linear differential equation. Okay? How to get an integrating factor. This is a very important part of the lesson right here. Given the standard form of the linear first order dE, that's what we said a minute ago, the integrating factor is e to the power of the integral of p of x. E to the integral of p of x. Whatever this function is in front of y, you're going to integrate that. It's going to be your power of e. But we're going to get some tricky algebra there. Tricky algebra there. E to the integral power of p of x. Now here's what's cool. Once you find your integrating factor, I call it I of x. That's my integrating factor. Multiply both sides of your dE by that. If you pick your integrating factor correct, then every single time, no matter what, this right here, on the left side, the integrating factor times what you got here, ends up being the product rule. Y'all remember the product rule from calculus? F prime g plus f g prime? It ends up being the derivative of the product of the integrating factor and y. Every single time. If you pick the correct integrating factor. The left side always becomes whatever your integrating factor is times y prime. What would happen when I integrate that? If I integrate something that's prime. A prime means a derivative, right? What happens if you integrate a derivative? It just goes away. It's like undoing it. Undoing it. Then you integrate this side also. Okay. Now integrate both sides separately. So, this is the steps. You might want to go back and look at this later, but right now let's show it in practice. The most important thing I can show you about linear is the integrating factor, how to do that. e to the integral of p of x dx. This is a first order linear differential equation, but it's not in the ideal form. Can anybody help me get it in ideal form? Yeah, you just want the y prime and the y on the left side. Make sure you get the y prime and the y on the left side. That's the main thing. What is your p of x in this problem? Remember, this is the form you're looking for. dy over dx plus p of x times y equals, what do we have over here? Q of x. In this problem, what is p of x? Negative 1. What's in front of your y? The coefficient of your y is negative 1. Okay, so my integrating factor I of x is equal to e to the integral power, integral of negative 1 dx. Now, I know it's late, but try your best to tell me what the integral of negative 1 is. Negative x. Hallelujah. Look at them go. E to the negative x. That's it. That's your integrating factor, e to the minus x in this problem. Okay? So what we're going to do is multiply both sides by it. So e to the minus x times y prime minus y equals e to the minus x times x plus 5. This is a beast of a problem right here. As I was telling you earlier, when you multiply the integrating factor on the left side, this always becomes the product rule. So it's an integrating factor times y prime, always. And I can show you that if you distributed that right there. What is that? E to the minus x times y. If I was going to do the derivative of that with a product rule, f prime g plus f g prime. If you were to distribute that right there, what would you have? E to the minus x y prime minus y e to the minus x. Is that not the same thing? Exactly the same thing. It's always going to, I'm going to show you at least once if that's what happens. On the left side, you're going to end up with e to the minus x times y prime. Prime. Now, over on the right side, it's not as nice. You're going to distribute that, so that's going to be x e to the minus x plus 5e to the minus x. Integrate both sides. What happens when I integrate something that's primed? The prime just goes away, so I've got e to the minus x times y equal to, okay, Maybe y'all have already figured it out. I'm going to go to my scratch board over here, my scratch paper. How in the world do you integrate? I can integrate 5e to the minus x. That's easy. How do you integrate x e to the minus x? It's parts. It's not going to be too complicated, I promise. Say, sure. Let's see. If I was going to do parts, how would I break that up? I need a u and a dv. What's the most complicated part of that problem that you can integrate? E to the negative x. I can integrate that. That's easy. And so the u would be my x, right? So du would be, what's the derivative of x? Derivative of x. 1 dx. And v, what would the integral of e to the minus x be? Except, what would your compensation be on this one? God, it's late, isn't it? U would be negative x, du would be minus 1, so your compensation would be minus 1 also. So it's going to be, you're almost right, it's going to be minus e to the minus x, okay? So let's see, who knows at 5 minutes, so 8, who knows the integration formula for integration by parts? UV times minus integration of v to u. I think you said it exactly right. So u times v, that's going to be minus x, e to the minus x. Okay? So minus the integral of v. du is just dx. I like that. It means I don't have to do it a million times. Minus minus makes a plus. So minus x, e to the minus x, and the integral of that we've already done. Integration by parts on that first part there. So we get negative x e to the minus x minus e to the minus x. And I'm not through. What is the derivative of 5e to the minus x? Plus c. Fit that in the screen if I can. Yeah. No, you should have to do compensation. The only thing is normally you multiply by the reciprocal of the derivative, but the reciprocal of the minus 1 is still minus 1. Yeah, so you'll have to do that. Compensation. Hey, those can be combined, can't they? Negative e to the minus x minus 5, that'll be minus 6 e to the minus x plus c. Okay, guys. Now you can solve that. You should always be able to solve a linear one outright. Solve it out for y. Explicitly for y. So what do I need to do? Divide through by that e to the minus x, right? Divide through by e to the minus x. Or some people say multiply through by just e to the x. Multiplying by e to the positive x is the same thing as dividing by e to the minus x. So that would be negative x minus 6 plus c1 e to the x. Look at that carefully. See if you see what I did. divide this e to the minus x out of everything. We went away with that one, so it's just negative x. Divide it out of that, which is just minus 6. Dividing it by c. C over e to the minus x would be like pull it up top. C times e to the positive. That one was horrible because they didn't break my parts. I would agree to that. Parts. Okay, let's do one not so hard. Is this in the preferred form? So I'm going to multiply, do what I need to do. Divide through by x. Divide through by x, first step. My integrating factor is e to the integral of what? I love this. This is where we got to get our algebra straight. What's the antiderivative of 4 over x? 4 ln x. Good job. Now this right here is where students go berserko on me and mess up. You got everything in the stupid problem right except this step right there. I erased the log laws off. What is e to the 4 ln x going to give me? X to the 4th, not 4x. Remember, if a 4 had been pulled out from the logarithm, that was actually a power. So e to the ln x is x. If this will be e, it'll be x to the 4th. So my integrating factor is x to the 4th. Multiply that times both sides. So x to the 4th times y prime plus 4 over x y equals x to the 4th times x squared minus 1. We know if we multiply that left side that we get that product rule. It's x to the 4th times y prime, always, equal to x to the 6th minus x to the 4th. Distribute that x to the 4th. Integrate both sides. So tell me what I'm going to have here. Y'all tell me on the left that the integral is going to undo the prime, right? So x to the 4th times y. Okay? Plus c, right? Power rule. Who can give me the answer? Divide through by y by x to the 4th, right? Divide through by x to the 4th. So that's going to be 1/7 x to the what? Third, okay, minus 1/5 x to the, it's x to the first, okay? Plus C1 over x to the fourth. That is a linear differential equation. Okay, to finish the night out then, finish it out. I thought about letting y'all do a work together, but I'm just going to do it with you because this is a tricky one. Not tricky, tricky. I love these. I know. I've tried to get the geek out, but I can't quite do it. Well, you know what? I think I'm going to switch gears here. I think I'm not going to do this one. I think I'm going to do the next one and save this one for next week. Okay, I'm going to save this example for next week to review my linear problem. This is a good one to review. Let's do this hard one to end the night on. This will be better. Okay, looking at it, first of all, this is a linear problem. Is it in your ideal form? And to get it in your ideal form, it's going to be pretty bad, isn't it? You're going to have to divide by that quantity, x squared plus 1. So this would actually be like so. Okay? So my integrating factor is equal to e to the integral of x over x squared plus 1. We may need to go over to the scratch paper here to get that all worked out. The integral of x over x squared plus 1. One goal I have for you guys before you get out of here is that you can integrate better in your head. Some of y'all may have that already down pat pretty good, but in Cal 2 and 3, when I talk Cal 2, at the end of the semester, I want some of those integrations to have memorized. We get to do it so many times, like trying to integrate the square root of x. We did that so many times, I'm thinking, gosh, you know that one. Okay? Well, you can get where you can do it in your head a little bit better. But the integral of x over x squared plus 1, how are we going to approach that one? U would be your denominator, right? So your du will be 2x. You have the x. You do not have the 2, so we're going to do a 1/2. So that becomes 1/2 times the integral of 1 over u. So what is the integral of 1 over u? Ln. So we have Ln, we have e to the 1/2 Ln of x squared plus 1. It's late, but can y'all figure that? Can y'all tell me what to do here? What that's going to be? The square root of x squared plus 1, or x squared plus 1 to the 1/2 power. The e to the ln part cancels out, right? but the 1/2 becomes the power. In fact, I think I may need to work with the 1/2 power instead. I'm not sure on that, just to make it make more sense. Okay, so multiply by the integrating factor on each side. Okay, on the left side, then we should get the integrating factor times y prime how in the world is this one going to clean up? Do y'all know? Not yet. Not until you get through with your integration step. You got to integrate on both sides first. X squared plus 1 to the 1/2, that will cancel with x squared plus 1, but what would my power be left? 1/2 on bottom. So that would be x over x squared plus 1 to the 1/2 when you multiply all that out. So we integrate both sides. I don't have another slide. Dang. Okay. If we could just integrate this right side. Same thing, right? U would be x squared plus 1. Du would be 2x dx. So I'm going to have to compensate with 1/2. But you end up with u to the minus 1/2. U to the minus 1/2. Okay, so I need a little help now, guys. Antiderivative of u to the minus 1/2. Negative 1/2 plus 1 is u to the 1/2, right? Divided by 1/2, which is times 2, isn't it? Or you could actually do this. So your antiderivative ends up being u to the 1/2, which is x squared plus 1 to the 1/2 power. Plus c. So, what's my answer going to be? If I divide through by x squared plus 1 to the 1/2 power, what's going to happen on this term? When they divide out, how many times will that go into if I divide this out? 1. First term will be 1. Okay, plus, how about c sub 1 times x squared plus 1 to the what power? negative 1/2. Or you could actually put C1 over x squared plus 1 to the 1/2. That's also a possibility. Okay. I have not yet made out the test for next week, but this is what I'm guessing. I want you to go over your first quiz that you got back. The majority, the highest percentage of questions are going to be separation. Separation of variables. Some review questions may be on there. Now, how about, let's put on there one homogeneous question, and I'll try to get one that's not hideous, possibly one that's on the homework or one I've worked in class, okay? Because you hadn't had a lot of time to digest that yet. One exact question. And if I put a linear on there, it's probably going to be extra credit. So, next week, what I plan on doing, the agenda is to come in and review separation, review homogeneous, review exact, review linear, and then we got one more little thing in lecture 4, the Bernoulli equations. I want to teach those and have a test. So like one example of each, and then do Bernoulli equations and then have a test. That should make it for a pretty good time spent next week. Okay? Good job, folks. Thank you for your attention.